I'm delighted to introduce our IDSS distinguished speaker, Professor Alex Bayen. Professor Bayen is a Lia Cho Professor of Engineering at Berkeley, both in IDSS as well as Civil and Environmental Engineering. He's also the director of the Institute of Transportation Studies, apparently an institute similar in nature to IDSS, with 7 research centers, but focusing mainly on transportation, as well as he's the director of the Transportation Initiative at the Lawrence Berkeley National Lab. He has very broad research interests in the area of control, optimization, estimation of distributed parameter systems, focusing on both traffic applications, but also on water systems. I guess one of the focuses of his work is very interesting, thinking about data-driven, or rather mobile phone data, user content, user-generated data, in the sort of control optimization of these distributed parameter systems. So he has many, many awards. I won't be able to read through all of them. I just want to highlight one, which is very, very interesting. His projects on mobile century and mobile millennium, which is exactly sort of using this mobile data to construct traffic, received the 2008 Best Innovative Practice Award from the Intelligent Transportation Systems and Services. And he has many, many awards. I can't think of a better person to speak in this series in IDSS, so please join me in welcoming Professor Bayen.
Thank you very much, Azu, both for the invitation and for the very generous introduction. Thank you, Pablo and Munter, for the invitation. I'm really grateful to be here. It's really an honor and a privilege. And I'm also very excited to see a lot of familiar faces, Hamza and Saurabh and many others in the audience. Today I'm going to talk about distributed learning dynamics, convergence in routing games. And I'm going to start with a kind of a general overview and maybe a bit of a history on traffic, mobility, and then later we'll do a bit of a deep dive into the type of work we do. So if you think about the history of traffic monitoring, back in the days when the government was providing you with everything you need, the mentality was that you would basically monitor everything with dedicated infrastructure, whether these are cameras, whether these are sensors, wireless or not, or even stuff in your car. And it's interesting to look at this graph, which shows the emergence of devices over time since the 70s. I mean, you will recognize stuff that probably most of you are too young to know, like the Atari computer or the Commodore computer. Macintosh, not even referred as like the first box one. What's interesting is this curve here, which is nearly vertical, which is the rise of the Android phone, effectively started in 2009. So historically, where this story starts is somewhere here around 2007. This curve is interesting too because it shows the penetration of the different devices today in the market. Of course, most of you have either Androids or iPhones these days. Maybe if you're interested in technology, you have a Windows phone or some other exotic brands. But OK, so you can see the penetration rates here. What's interesting is that when this story started back in 2007, the N95 and the E71 were the devices of the moment. So having an accelerometer, a gyro, and several other sensors on board the platform would be what did we want to do? Whatever you have to do with me. It's just like TSA, you know. Whatever TSA says when you go to the airport, you let them do, and then you don't get in trouble. So we started getting interested in that problem right here, which is a time when the iPhone did not have a GPS. You probably remember the iPhone 1. And it was a year before the Android was born. And so the story starts, and this is the outline of the talk. First, I'm going to talk a little bit about mobile millennium, which is how I got into. I was not a transportation person. I had never done anything to do with ground traffic. But that's how I got interested in it. So the first 10 minutes will be kind of a historical perspective on how we got where we are today. If you just like math, this is a good time to sleep. Because we'll take a deep dive into some of the algorithms in part 3, which if you don't like math, would be also a good part to sleep. And then I'll talk a little bit about what we will do in the future. So mobile millennium was the first traffic app that ever run on RIM and Symbian platforms in North America. RIM was basically the BlackBerry platform, and Symbian was the Nokia platform. Both of these are nearly defunct today. At the time when we launched this app, which on this phone looks almost like a vintage device, this is what it looked like. We were very happy because locally around Berkeley we had 5,000 downloads, which later were scaled up by Nokia as a company. And within a few months, we started collecting GPS data to populate this map, which you see here. This is probably the first time historically that people could see arterial traffic based on GPS data. So again, looking at a vintage website in 2008, if you wanted to have information about traffic, you would go to 511.org. And in Boston, you would probably get a similar display, so mostly static sensors giving you information on the freeway. And then by 2010, we had this map running before Google launched it, 3 days before, I think. So we were 3 days ahead of Google. That's probably my only claim of fame ever. The thing here was that most of this information at the time was generated by GPS-enabled smartphones. So it was a long process to build this. We started in 2007, late 2007, and because this was mostly funded by the DOTs at the time, they wanted a proof of concept to show that with a certain penetration rate, you could make it work. And we hypothesized back in 2007 that with 2% of people like you and me carrying these devices and transmitting data at a given frequency, you should be able to make it work. We showed it in simulation, but of course they wanted an actual proof of concept to see it work. So we actually hired 200 students to run a field experiment with 100 cars and asked them to drive for 10 hours back and forth on these 10 miles of freeway. Of course, they would take turns, right? They would be given free food and a free TV room and a lot of goodies to relax during the break times. But the idea was to maintain a constant 2 penetration rate on the freeway. So this is probably the first time in history. These are, at the time, I was just being released from the military, so it was like almost like back in the days running a military operation on the ground. We had a command center run by a former colonel of the Egyptian army, like really tough guy on security. It was awesome to work with him. And then we had camera crews on the bridges, really running this pretty tightly with points where we would collect data on every license plate of every vehicle going on that freeway on that day, so we could reconstruct travel time and have an actual validation data set completely independent from the smartphones. And so the idea was to show that we could do it. So we held a press event with the CTO of Nokia at the time, Bob Iannucci, came in from Finland for this, and the director of Caltrans, Randy Iwasaki. And this is probably the first live display ever of traffic information broadcasted strictly from phones. In fact, there was a press conference, and the journalists were looking at it when we launched it. And what you see here is something which looked like an accident at the time, and we didn't think it was an accident. And the person here used to work at a company, which is also defunct now, called Traffic.com. And what she's doing on that picture is calling Traffic.com to check that what we were broadcasting was probably correct or not correct. And because people could see the freeway, they wouldn't believe that downstream 2 miles there would be such a pileup accident. It turned out that there was a 5-car pileup accident on that day at that location, and we ended up catching it about 15 minutes before the police did, because at the time they still had pagers, another defunct device, that beeps every time there's an accident. So of course the rumor then started that the Berkeley people created an accident to demonstrate the traffic. Because I wouldn't say this is an MIT rumor, I think it's a Stanford rumor. So we ended up rebuilding the system 3 times over the years. And basically ended up building what was the first prototype ever used industrially by Nokia at a time when they were competing with Google and Apple to do that. So, having feeds, fuse heterogeneous sources of data into filters. If there's someone who has another laser saber Star Wars style, I could benefit from it because it's not working much. I don't know if you have another pointer. Then this would feed it into models. I don't know if you can see anything, so I'll just keep pointing with my finger. That would then feed estimation procedures that could enable us to do forecast and finally inform people about the state of traffic. This is what about 0.5% of the traffic was looking like at the time. Here, every red dot is a taxi. We ended up having a lot of sources from all the taxis in San Francisco. And thank you. And Black dots are the GPS track left behind at the frequency of 1 minute. So that gives you a sense of the data we were dealing with. And just for reference today, Uber has about 2,000 vehicles at a given time hovering in that area. So you can see how this data in the meantime has exploded. If you let the movie play the whole time, you'll end up with something like this, which is amazing because you can see within a day, you can pretty much build an entire map of the entire city. So we got really excited about what you could do with 2% of the driving public here. And the name of the game is with 2%, that's roughly what you get. So with 2% of traffic, so this is time and this is space. Each of the dots is one GPS track, and the color indicates the speed. So blue is about 70 miles an hour, and then red is the traffic speed, so I don't know, like 10 miles an hour. So you can see the accident I referred to before happening in the morning, being resolved, and then the congestion of the afternoon rush picking up again. At this level of penetration, you can pretty much read the traffic, though there's issues with it. So what we were trying to do at the time is see if you decimate the data, so you have now way less than 2%, could you construct estimation algorithms that enable you to reconstruct the data? So for a couple years, we built these algorithms, and just to illustrate you graphically what they look like, once you reconstruct it from ensemble Kalman filtering or other particle filtering techniques, that's what you would get. Okay? So you start from data which you can use for validation, you decimate pretending you have way less data, you reconstruct it, you validate that the data is good. We happened to run it against Google at the time. And what we were able to show is that at the time when we launched the system, we were producing traffic information about 15 minutes faster than Google. This is illustrated here. There's an accident that we detect. Every frame is 30 seconds, so obviously otherwise watching traffic is pretty boring. But you can see that now we detect traffic, and on Google it still shows green, when ultimately they will finally broadcast it with a level of accuracy that can be debated. Like now the accident appears, and then ultimately they show some congestion here. So of course, nowadays, any company in the world is using GPS information. But at the time, it was also very nice to see that with this, not only you get faster, but you get much better information.
So this is real-time information, not predictive information.
This is real-time information. So in real time, we were 15 minutes earlier than the competition. So, and that brings me to kind of the timeline of this project, and which is a long introduction to today's talk. So, at the time, the giants of the time, Nokia and Navtech, were ruling this world, and today Nokia has moved to very different things. What's exciting is that over the years, as the project evolved, we got engaged with other companies, Telenav, which used to produce all the navigators in your AT&T phones and many other companies. But ultimately, Apple hired several of our group members. So did Microsoft, so did Google. The person running traffic at Apple today is Ryan Herring. He's a former student of the group, and basically the one who architected the whole Mobile Millennium system, the first generation. And then now we have a lot of other companies who have hired people as well. So once they cross the border, we know less about what happens to these systems. But it's really nice because all of these companies today are collecting a lot more GPS information that we could have dreamed in 2008 or 2009. And certainly, we recognize a lot of the things in the products we see coming here in the market in what we did before. So now it's 2016. It's nearly 8 years later. And we see that we're nearing, we're not there yet, but we're nearing a situation in which you have probably at least one phone per driving adult in the United States. So the next question we worked on back in 2010 and 2013, until 2013, is could we help the state buy this data? Because now this data is available. Of course, Google will not sell this data, but a lot of other companies will sell this data. And so one of the things we did is we helped them with the first ever public procurement of the data, of GPS data done in California. So the state wants to buy data, they don't know how to buy it. So, and along with that is the issue of data quality. What defines good GPS data? So GPS data that is more than 5 minutes old is bad for traffic operations. It's probably very good for planning. So here's an example of a dashboard we built for the state of California in which we show them that if you happen to buy this type of data, well, you can never use it for operations because 5 minutes from the time it's collected is probably already stale. I mean, you can see from the previous example I gave with Google. But other things we came up with is interesting because, for example, some companies were selling data where they're saying, OK, I'm going to sell you 1 million data points a day for these 10 miles of freeway. But that's probably useless if this data is collected at night because you're a trucking company. And so we had to come up with all these metrics to help them do that procurement. And that was interesting because, in a sense, it was the last mile in this first stage of the project. First, we built the prototype. Then the industry caught it. It was nice. And then finally, we helped the state to buy it. And I think today you could accurately say that this is a very mature field, and that's why we moved to other things. But in the process, over these, I don't know, 5 or 6 years when we were working on it, there were a lot of contributions we had to make to modeling because integrating mobile data in flow models was new at the time. There were a lot of contributions we had to make in estimation because making filtering algorithms that work with these PDE models was not easy. Of course, we had to do a lot of experiments. And we ended up defining metrics which are used today in public policy to buy this data. So I think the circle was almost complete. And then we decided to move to other things. So just like I showed this, the next stage was like, OK, now that we can do estimation to reconstruct this, can we also do control? And thank you so much. And the ultimate, so now I can do a dual. Thank you. So now that we can do estimation, could we do control? And the ultimate proof was executed by Seb Martin, who is right here, before he came to MIT. And to show this, we showed that we could recreate any pattern on the freeway. So we chose the Cal logo, of course. I'm sure you guys would have done the same. And the notion here is that assuming you could control all the traffic lights the way you wanted, say you're a super hacker, and this has been kind of done not only in movies, you could basically create congestion on demand just for the fun of it. By the way, we have a reviewer who is so angry at this that he keeps rejecting our paper. It's like the 5th or 4th review. And I don't know if this is because he's a competing university or it's just because philosophically, I don't know, it doesn't capture. But the point here is even though we don't have controllability of the system, because it's a set of networked hyperbolic first order PDEs, so we don't have proof of controllability, there's a lot of algorithms that can do that well. So there's a lot of research in the field of control for these models, and this is something we have engaged in because there is a need for it, not for hacking purposes, obviously, but for real control purposes. And so one of the things we're helping the state with is building a system that can control traffic at a much bigger scale using these types of models. So you could view Mobile Millennium as the little box here, the yellow box, which is the estimation piece. And now it's becoming part of a much bigger engine that we're building for California, which does prediction and on which you can apply optimal control. So, of course, when you think about optimal control, it's not just the freeways, it's the arterials. And so this is an example on the I-210 corridor in Los Angeles of all the control points you have. So every traffic light in that corridor ultimately will end up being controlled by a single system so that you can start to balance the flows. And you can view this as a real traditional way of controlling traffic. And I think until a couple years ago, you could argue that this is really the only thing that the state could do to make traffic flow better. Except if you look at what's happening everywhere in the world now, this is going to be less and less the case because the government is progressively losing control over mobility. And that's because all of us are using apps that will do things which every company is telling them to do. And that things like the changeable message signs or the ramp metering are only going to affect less and less of your mobility patterns. And so that brings me into the theoretical core of this talk today. The one thing I'd like to understand in the future, and we're just scratching the surface here, is how do people react to information? So over the last 10 years, you could argue that there was a race to produce that information. And everybody more or less succeeded. Today, Google Maps, Apple Maps, InRix, everybody has a map that gives you traffic information. And there's multimodal routers which tell you when the bus is coming and the availability of seats in the bus and all that stuff. And so that is changing the way people behave. Then you add Uber and Lyft on top of it, which potentially can help solve the last mile problem. And now mobility is going to change greatly. So this is very disturbing to a lot of planning agencies because classical mobility models are falling apart just because mobility patterns are changing much faster than they used to do in the past. And so I'm going to first present a mathematical problem that attempts to capture that, and then I'm going to try to give you some relevance of why I think it's an important problem, and then we can see the results that could be derived from it. I apologize, the colors are not quite as nice as on my screen, but hopefully they're good enough. So imagine you had the ability to route anybody you wanted from where they live to where they work. So I know that only happens in North Korea, but say you had the ability to do it here, then you would be in charge of basically allocating from any origin to any destination. You would have to allocate people along different routes that they can choose, okay? So P is your distribution, and X are your flows, K is your population from your origin to your destination, and you're in charge of routing this population. And at the end of the trip, or at the end of the day, as everybody has moved from their origin to their destination, people experience a certain cost, latency, which is basically how much time they spent in traffic. So now people react to this. So if you're in charge of these people and you see how your people did, then at the end of the day, you try to do something better for the next day, which means basically your next distribution on the next day at t+1 will be a function of what it was today and the outcome of what it was today, okay? So at this point, it's a mental abstraction. This has no connection whatsoever with my traffic picture, but it will have in a couple slides. So just think about this online learning algorithm in which at every step, you allocate your flow. You're the master of this flow for this population K, and that's true for every population. You discover your cost at the end of the experiment, and then you basically update the next day based on how well you did in the previous day. So in a sense, you can view this as a learning algorithm in which you discover the outcome at each of the iterations. Okay? And obviously, your outcome is linked to how other agents are doing, because if everybody wants to take the same road, then that's going to congest the road, so the cost is going to go up. And if nobody wants to take that road, then the cost is going to go down. So your outcome is not only depending on your action, but on the action of the others. Right, so let me reconnect that to my previous picture, and then we're going to go deeper in the algorithm. So I mean, think every time you open Google, Google probably gives you 3 routes, minimum. So they give you a preferred route. This was one I did a couple days ago to go to Stanford. And then they give you another route and a third route. And if you look here, I mean, 55 minutes, 58 minutes, and 56 minutes, I mean, to me, that's nearly equal, because 3 minutes, this is noise. So the point is that any app today will give you the 3 shortest path, or the n shortest path, and it'll be nearly equal, most likely, based on the options available. Here it's a bit more drastic because there's bridges, so in a sense you have discrete choices. But in general, you pick 2 points really far apart, you'll get very similar arrival times. So, and note also that when these companies do that, they don't forecast necessarily to the fullest extent what traffic will be. I mean, the forecast models are based on statistical samples they have collected over the previous years, probably some forecast model based on the statistics, but it's unlikely that all of these companies have a full dynamic traffic assignment model that takes into account future demand to solve it. It will probably happen in the future, but today, this is mostly information based on the past, and maybe some on the anticipation of the future. So you can view all these companies competing for the same resources. So Apple, for example, will decide to route 60% this way, 3% this way, 37% that way. Okay? And roughly on every route, it'll be the same travel time. And then Google, which has probably a different algorithm, or Waze, and now they're the same, will route 40% this way, 54% that way, 7% that way. And because they are similar technology, it's likely that the travel time given to you by Apple or by Google will be nearly the same. So in essence, what all these companies are doing is they're providing you a solution which looks like a Nash equilibrium. And I say looks like because there's a lot of issues here. But if you think of getting the shortest path, whatever app you're using, in a sense, you're going to get the same result. Now, shortest path is a selfish solution. It's not a part of a system optimum. It just gives you what given the traffic is better for you individually. So you can view these companies, which have nearly achieved like a monopoly, or like I don't know how to say this in Greek, but basically we have split the market differently. So probably Google has maybe 60% of the users, Apple probably 30%, and then the others share a smaller fraction. And they're all competing against each other because they don't really collaborate. So in essence, what happens is exactly what I showed in that learning process. Based on the previous way, in the previous days and the statistics, they're going to try to do the best outcome for you the next day. So they're essentially playing this game. And that's the game that I'm interested to model and to understand because people react to this. And so there's a lot of questions here. First, does that process even converge to an equilibrium? If so, under which conditions? Of course, then you have all the typical, once you establish convergence under some assumptions, what about robustness? What about different learning rates? I mean, some companies might learn faster, some companies might learn slower, some companies might just do the same forever. And then, of course, there's a lot of issues about continuous versus discrete times because at some point, it's actually easier to model things in continuous time, but the results here are discrete time. So the general problem formulation is, could we define a general learning class that would be proven to converge to something? Something obviously will be a Nash equilibrium ultimately, but we don't know this ahead of time. So here in this thing here is like, can we design a class U such that ultimately this iterated solution to that problem converges to the set of equilibria? That's the general question. And remember again, I mean, that's basically UK is the business in which you are if you're a routing company today. So what is a Nash equilibrium here? A Nash equilibrium here is basically a solution to the problem in which there is no incentive to deviate from your path. You know, why would you use Google if Google gives you something which is not as good as another company? So every company should give you the best, otherwise you're going to stop using it. Which can be translated in here, which is saying that the dot between your latency vector for all the flows, for all the populations, is such that when it's dotted with a deviation to it, then it's not as good as taking the optimum. Okay? So standard definition of the Nash equilibrium, which in the specific case of the routing game, using the Rosenthal potential, can be also written in differential form. In that case, that means that basically this L function for all the different costs is the gradient of the Rosenthal potential, and which has a tangential interpretation here. So it's a pretty standard definition. Okay, so now the main game here is, this is the game that these companies are playing. Can we define a set of assumptions on that game so that we can guarantee something? Because at the end of the day, you know, the government is losing the control over what's happening. These companies are taking over your mobility, and you're very happily participating because it's good for us. But we don't know, you know, what this will produce. So I'm going to go through three approaches which are interesting because each of them gets more and more restrictive in the assumptions it suggests. And of course, with more restrictive, then you can get more guarantees on the convergence of these algorithms. So the first one is the no regret policy. And you can define the regret as comparing yourself to the best thing you could do if you kept playing the same, which is essentially what this formula tells you. So you have the regret, and you compare yourself to a single strategy, and if you played always the same, and of course you take the best among them. And then you scale it by t because you keep playing that game, so obviously you have to scale it. And so the class of sublinear regrets defined by this provides, and this is not from us, this is from a long time ago, a proof of convergence of the average to a set of Nash equilibria, which means you have no guarantee on what's going to happen, okay? But you know that on average, if you keep taking the average over what you do, you will ultimately converge to a Nash equilibrium. So this is very good if you do optimization, because then all you need to do is to keep track of your average. But operationally, it's a bit problematic. So take a simple example of a graph. So you have two populations going to the blue, from the blue to the blue, and from the red to the red. What can happen in this case is if people behave this way, so basically if people play the game I explained with Google, but the only assumption you make on that game is that there's no regret, then you can have oscillations. And so what does that mean? That means that on Monday, you take this route, and everybody takes this route, so it's congested. And on Tuesday, you take that route, and so that route gets congested, but this route is free. And on Wednesday, you take the first route, and the whole thing could oscillate forever. So basically, you can see population 1 oscillates between routes. Population 2 oscillate between routes. And in average, sure, it's OK. The cost will converge because you take the average. But of course, in practice, it'd be horrible. So it's interesting because it says that if this model of learning is what people are doing, you could have enormous instabilities where one day Google decides to do this and they realize, oh my God, this was horrible. So the next day they decide something else, and then you have these instabilities. Notice that though these algorithms initially came in the context of optimization, so it's not necessarily a bad thing for optimization if this process models an optimization algorithm, but if you use it to model routing, well, it means that this policy is a bad policy. So the next approach is to look at this update equation, the game that these companies are playing, as the discretization of a known ODE. And the nice thing is that there is an ODE known as the replicator equation, which is here, which, if discretized properly, basically comes up to be a known update equation, sometimes referred to as the hedge algorithm, and it can be discretized in many different ways and lead to other discrete equations. So the way to interpret this replicator equation is that, so it's an ODE, it's again an abstract construction, in which the rate of change of your flow allocation on an arc is proportional to the value times how you do compared to the average. And so you could view it as a P controller in a sense. So if it becomes bad, then it brings you back. And if you do good, then it forces you to do more. And if you discretize it in a certain way, then it results into something called the hedge equation, in which your decision at t+1 is whatever it was done before multiplied by a correction factor, where inside the correction factor, you have your outcome, which is L, so that's how much you experienced in the previous iteration, multiplied by eta t, which could be interpreted as a learning rate, okay? So for example, if eta t is very large, it will amplify the effect of L, so you learn fast, and vice versa. So for example, if you do very poorly, because say you have a very large L, this will be nearly 0, which means basically you should stop allocating people to that route because it's a bad route. And if you do really well, because L is small, then that will be closer to 1, which means you should keep playing the same thing because that's good for you. Okay, so this is called the hedge algorithm. This is the replicator dynamics. And one of the things that can be shown is that if you discretize it in a certain way, which is shown here, so using forward Euler in time with respect to time, and then adding some noise, which I'm showing here, satisfies some specific assumptions, then you can prove a stronger convergence. So for that, you have to make assumptions on this U noise that you're adding to it. So it has to satisfy this property, and also it has to satisfy some asymptotic properties, which I'm showing here. It's a technical feature needed. But the benefit now is that you can prove convergence. And just to give you a sense of how this is done, the way you do it is you discretize in time, and you show that at every time, ultimately, your continuous trajectory ends up being in a ball that is closed to the discretized trajectory. Okay? And if you make the additional assumptions on the learning rates that they have to go to 0, so ultimately you've got to make up your mind. But in a certain way which is not too fast, so that this is still a divergent sum, then you have this almost sure convergence here. So the proof, I'm not going to show the proof today, but the idea of the proof is that you keep having this convergence to a ball, and then you use a limit argument to prove the convergence. So this is what it looks like in practice. You can't really see the grid, I'm sorry, with the quality of the projector. But in blue, you have the continuous trajectory, which are shooted from the discretization points. In red, you have the discrete trajectory plotted from point to point. And basically, asymptotically, they converge to the same value. So now, just in conclusion to that second part, this is good because now you know you're converging to Nash. You still have no convergence rates, but you know you're converging to Nash. So if these companies I'm talking about, and we don't know this because we don't have the data, behaved in this way, so if the way they behave follows this assumption, then at least we would know that, well, it's not too bad now because you cannot have these oscillations, and there's convergence to a Nash equilibrium. Now, if you push this one level further and you make even stronger assumptions, you can prove a stronger convergence. And so here, the third and last way to look at this problem is to think about it as a distributed algorithm for a convex optimization program. So think about optimizing a function f, so in the case of routing games, your Rosenthal potential, subject to a convex compact set. Okay. There's something called the mirror descent algorithm, which is a very standard algorithm to solve this, in which you use the Bregman divergence to define the steps. So this is the definition of the Bregman divergence. You take a strongly convex function and write this way. Then mirror descent can be summarized this way. So at every step, you pick a point in the subgradient of your function, if it's not differentiable. And then you solve at every step this optimization program. Okay, so in appearance, it has nothing to do with your problem with Google Waze and so on. But it turns out that if you make a specific choice of the Bregman divergence with a KL divergence, so using an entropic psi function, well, this basically can boil down to the hedge algorithm. So in essence, you're saying, if my companies behave this way, so if the choice of the company at t+1 is modelizable, can be modeled as an update step in this mirror descent business, where eta t is still my learning rate, then I have convergence guarantees, which I'm going to show next. Okay? So of course, again, we don't have the data today to check whether that's the case, but the benefit of this is that this algorithm is centralized, but it can be decentralized. So now every population running it independently according to the same learning paradigm I've shown before. And it can also be put in a stochastic framework in which you don't have a perfect value for your loss, so but you only have an estimate for your loss. In that case, it's stochastic mirror descent. Okay? And so the benefit of this is that if you choose this approach, you can actually show that you have convergence. So in order to achieve that proof, obviously you have to prove some intermediate results, which again have some technical conditions here. So again, the learning rates cannot decay too fast, and they have to be L2 summable. But provided these assumptions are met, then not only you can prove convergence, but you also have a rate on the convergence. And the rate on the convergence is not only on the value of f, so in expected value, you can prove that your process will converge to the optimal value. Again, remember, Paul Rosenthal is a convex function according to this bound here. And obviously you have to make choices here. So the choice you have to make is you have to choose a learning rate, which is whatever it is. In that case, if you adjust your learning rates properly, you can prove this convergence. So it's interesting because it's a much stronger result. And by the way, the convergence is not just on the value. I'll show it's also on the value of the state. So you can quantify how fast the state is nearing the equilibrium set. So going back to where we stand, this is a given model. I don't know if it's a good model or a bad model. I mean, this is, as I said initially, we're just scratching the surface here. But these models that I'm showing here, even though they are actually known algorithms or partially known algorithms for convex optimization or for repeated games, they are also a good constitutive model of what we think is happening when Google is competing against Apple and with all these other companies to route their populations. And so depending on the assumptions made, then you have stronger guarantees on the convergence. So just to summarize, if you just make a no regret assumption, then you only have convergence of the average. It's OK, but it's not great. If you make an approximation of the replicator dynamics as a discrete update system, then you have almost sure convergence. OK, it's better, but you don't have a rate. And ultimately, if you have if you view this as a stochastic optimization program, then not only you have convergence, but you also have a convergence of the state, and there's a bound which I just showed on the value, and there's a bound on the state which I'll show in 2 slides. So to give you a sense of, again, this in practice, if I go back to my specific example here, so blue population going from the blue to the blue, red population going from the red to the red with these specific learning rates. This is what my simulations look like. So now we have a much nicer result because you can see the populations do converge to their value. So for that particular example, there's 3 distinct paths. There's the green path. Nobody takes it. That's because it's longer. Then there's a blue path, and then there's a red path, which adjust themselves in a way that the travel times are actually equal. And then the green travel time is much larger, which is why nobody is taking the green routes here among population 1, and then you have a similar thing with population 2. So it's nice because this is just illustratively showing that these Nash equilibrium properties are verified experimentally, though obviously we knew it from proving the theorem. And then if you look at the convergence of the results, with that particular learning rate, which you choose for the players. Then you can show the convergence, and now this is not in value of the cost function, but it's in the value of the state, so it tells you how close your state is from the equilibrium as far as your x state is concerned. So this is measured by the, again, by the Bregman divergence, and again, you have a bound on the convergence. So of course, this is making the strongest assumptions. Okay, so will we ever know whether it's a good model of the way companies behave? Okay, today we don't have the data for it, but we tried it on humans, just to see, could we show that at least this is a good model to represent how people learn. So Walid, who is here, created a very nice game. So he's the one who proved all the theorems, so he can do also coding and proving. Very nice game that all of us can play. Hopefully at some point we'll release it on the web so we could have larger people playing, but right now it's just being played in the lab. Here, what the game does is it makes people behave as if they were Google, Facebook, Apple, whatever, routing people. So say there's 4 players. One will play Google routing a population a certain way. A second one will play Apple routing the same population a different way, and so on. And so then we want to see if we can use this to recreate what we proved in practice. So every player in the game has access to the network. So they're given a population to route, and their network manager, their population manager, and they can route that population from their origin to their destination. So the way they do it is they allocate people on different paths. So there's a bunch of sliders, and you can choose, okay, I'm going to put 30% of the population on this route and 40% on that route, and so on. Okay? And then as they play the game iteratively, they see their previous costs, or a subset of, we can show them more or less information depending on the assumptions we make. But basically, they can see their previous cost, so how well they've done in the previous iterations. They can see their cumulative costs, so how much they're doing overall. That's good for the regret. And of course, they can see their flow allocations. Okay? So for example, if I'm a player here, I can see my cost is doing this, and I can see my flows are doing that. So from a process perspective, what that means is that everybody is playing the same. Everybody is routing their population. Everybody experiences a loss, and they keep playing. And then we wonder, does that stuff ever converge in reality? Because there's a lot of nice assumptions here, but does it work in reality? And more than that, could we actually learn how people learn? So what does it mean to learn? Remember in this formulation I had, eta, which I'm going to zoom back and back, okay? There was something called eta, which was the learning rate. Okay, this thing here in the mirror descent, that's your learning rate. Okay, so if you're a very aggressive learner, you have a large one. If you're a slow learner, you have a small one. Okay, but it turns out that the process of fitting the proper eta to the data you have is actually a convex problem. So if you assume that this learning rate is unknown, because I don't know, Saurabh might be learning really fast, but someone else might be learning very slow. So if I don't know how people learn, basically I could try to minus this, and then find the proper eta that minimizes the match with the data. It turns out that that's a convex program, so that's something we can actually solve. So what we did with that game is we had people play that game, and as they were playing, not only could we actually see that they were converging to a Nash equilibrium, but we could also learn their learning rates. So it's like, now we're going to try to anticipate what people are doing in the game through that convex program. And the results are quite interesting. So at the beginning, when you look at what people are doing, you can see a lot of exploration. So I try 40% here, 40% here, and then I see, oh, it's not really working well, so I'm going to try 60% here and less there. So initially, you have people who try a lot of things, but ultimately it converges to cost, and it's all normalized because people have different origins and different destinations. And it actually converges quite nicely. Now, you can, a guy is still nervous here. So there's a guy who, even though he looks like he's converged, he's still very nervous and stressed, so he's probably trying to still explore a bit more, but ultimately keeps converging. And again, this is if you look at the cumulative cost here, so this is now the value of the game, this initial exploration phase, and then ultimately some convergence. So, it still doesn't tell me anything about Google, Apple, INRIX, and so on, but it's funny still because it tells me that if you put people in the same room and you have them play this game, ultimately that is a good model of their behavior. And you could also argue, well, could we use this to do a minority report and try to understand what people will do in the future? Could we use this for prediction horizon? And this is still something we're experimenting with, but it's interesting because you can fit different models now that you have your learning rate. You could say, I have a parameterized model. I know that people ultimately will get tired and learn less over time. Or I could say they always learn the same. Or I could say, well, I'm going to fit a linear model. So depending on the models you fit, you can see different prediction horizon and error. And of course, the further in time, the more error, because forecast always degrades with time. But it's interesting because at least we can see that these models do reasonably well over a short period horizon, which means at least you can try to see what people will do over the next 2 or 3 iterations. So this is cool. You can see people playing, and you can see that you can somehow determine from their previous actions what they're likely to play in the game in the next actions. This is obviously still open, and we're going to run much bigger experiment, but it's early enough that it's exciting to show. So before I finish the talk, I'd like to expand it to something which we're not finished with yet, which is, OK, now how does it relate back to practical problems, and how does it connect to heterogeneous games? So I go back to my scheme here, where these companies more or less share the market, and they're all more or less taking care of your mobility. So now everybody's happy to play with. And I'd like to take a more public policy approach to it and see, well, is it good or bad for society? And then is there any arbitration that should come out of this? So the general context is that there's a very vocal company that was acquired by Google. The company is called Waze. And Waze got on that bandwagon that if you provide people with the shortest travel time, which is essentially providing people with the option to play the Nash game, it's going to be good for society. Okay. All of you who play game theory are probably smiling. But OK, it makes the news. So people commonly believe that if they do the best selfishly, it's good for society. And it will happen so near you, because this happened in Boston, too. I just want to make sure that I make this clear. So very vocal things for Boston. Until people get upset because now there's more people coming in their neighborhoods, which used to be car-free. And people start to be really upset with these companies and start to rebel against these companies. And there's many ways to sabotage Waze. I mean, you could pay your grandmother to run along the street with the phone to pretend she's a car, stuck at 10 miles an hour. People do that. No, seriously, senior residents have done this in these neighborhoods. Or you could do what cities do. We were talking about with Monter this morning. I mean, he showed me the chicane-style streets design in Boston. The way they do it in California is more stop signs and more bumps. That way, your travel time degrades so badly that the algorithm learns to not go through your neighborhood. Great, right? I mean, if you're the mayor of a city, your value proposition is, I'm going to make traffic worse in my city to make sure that people don't come to my city. Okay. So, but this is the reality. And today, when you talk to a small city of 50,000 people, sure, they're not going to take on Google, who has probably 800 to 1,000 lawyers, because there is more cars in their neighborhoods. They at most have 3 or 4 lawyers on the payroll. So it is a real problem. And it has become very political. I was testifying to the assembly in California a few weeks ago. And I mean, these are the problems that are now mentioned in the political domain. And that's why I want to put the picture of John Nash here, because it's a real question. So, and the thing is, it's not a yes-no answer. That's the problem. So first, I mean, is steering mobility towards a Nash equilibrium good? Actually, probably yes. Because what's happening today is worse than a Nash equilibrium. That's because still a lot of people are not using apps. So that means a lot of people are going on the freeway anyway, even though the travel time would be much faster on the arterial road. So actually, steering the optimum toward Nash is probably a good thing globally. But obviously, it's not as good as system optimum. OK, anybody knows this here. So the real question is, if you displace the system partly towards a Nash equilibrium, what should be the arbitration process so that if society benefits as a whole, the local city who really gets a bad deal in that process, because there's extra traffic, doesn't suffer too much from it? And this is a real problem. This is an example of a simulation we're running. So say overnight, 15% of the people on the I-210 decide to use a given app. And this app tells them, OK, the best way for you is to go through Pasadena. Instantaneously, 17% increase in travel time through these 3 miles of freeway. So you can see how the city would get really upset here. I mean, a freeway lane carries 2,000 vehicles an hour. This is a 5-lane freeway. This could get really bad. And if you make the computations of the travel time, basically, here's what it looks like. This is 0%, so that's the Stone Age, 2007. Nobody uses a traffic app. And this is 25% of the people using apps, probably happening in the future within 2 or 3 years. And what you can see is that, OK, awesome for the freeway. OK, it starts really, really congested. The more people use apps, the less travel time on the freeway. OK, freeway looks cool. And then this is the city before this happened, the happy city of 2007. And then as 15% of the people use it, then boom, Nash. Now we have a Nash equilibrium. OK, but OK, you can see the city has. Yeah.
Right? These people know both the city as well as the freeway. So if you're thinking about Nash, equating flows on both, they know both of these options. So that doesn't look like an equilibrium.
No, it is. Well, no, it is an equilibrium because here there is no incentive to deviate. If I'm on a city and I go back to the freeway, obviously this is a simplistic routing case because you have a single origin, single destination here. So I don't consider the whole network. But if I deviate from the arterial, I go back to the freeway, the travel time would go up again. So I shouldn't deviate. No, well, empty. Okay. Empty is not completely empty. No. So, okay. So yeah, sorry. No, there are cars. There are cars. No. Okay. So empty was a figure of style to say it's smooth, but no. So obviously, no, the freeway is not empty. That's why there's cars on this picture here, and the city is not empty either. Okay. So it's equalized. Absolutely. So sorry. I'll change. I'll make it very clear. No. Just to, it's a true Nash equilibrium. There's flows on both. They're not the same flows. The travel time is the same, and any deviation from these flows result in an increased travel time on the other option. Absolutely. So sorry for not being clear. So I'm going to put the picture on because it is a Nash equilibrium. Very good. So there is a graph formulation for it. This time I won't do a deep dive. And I think it's the same framework as before. There is the same exact definition of the Nash equilibrium, except now it's across many populations. So the population are same. Regardless of the population you're using, you don't have an incentive to deviate. But the major different assumption with respect to the previous case is that now your cost function is your own. So for example, I might really not like to go through that neighborhood because I don't like that neighborhood. So I'll have a higher cost for that neighborhood. So travel time is not now the only metric here. And that's a good way to model the fact that some people might use an app and some might not, or some people might decide to use an app if it really provides some significant value. So I'm not going to deviate unless I get more than 10 minutes. And so on. So the main difference with the previous one is that now the cost functions are not only depending on the route, but they're also depending on the population. Now, the bad news here is that you cannot apply the Rosenthal game just like I did before, so the whole thing falls apart. That's why it's still somewhat open problem in the way it's going to be used. There are some properties that says that if you freeze all populations but one, the problem is a convex program. And ultimately, you can solve it by block-coordinated descent, which is what I'm showing here, which is nice because you still have a way to compute this equilibrium. So this is just very preliminary, but this is to show how the results I was showing for Pasadena were computed before. So just to bring me to some conclusions, because we're nearing the end, then I'm going to show just another 2 or 3 movies. The historical perspective is that in the last decade, one could really argue that technology has brought this information. 10 years ago, nobody in this room would have known how to route themselves other than dialing 511. Today, anybody can get that information on the phone. And so we still have not reached equilibrium because even though you all have that information, probably only a subset of you is using that information. So really the contributions in a kind of a post-travel time, post-control, optimal control era where this information is known is how you model the way this information is used with different costs based on different users, and how you model the way people react to what they see. I mean, Google gives you a really crappy travel time one day. How are you going to react to it? Or Google as a company realizes that by routing people in a certain way is not optimal. How do they react to this? Ultimately, these companies will probably end up solving a dynamic traffic assignment problem because I think there's no other way if you want to do good forecast, but this is still something to come. And certainly from a public perspective, there's a lot of interesting questions here because there is still no good answer to the city of Pasadena if there's going to be an extra 3,000 vehicles an hour, which increases the travel time by X%. First, who should pay for it? And then how should that be computed? So ultimately, these problems came from a broader class of problems that I work on, which are mobile sensing problem. I mean, I really embraced this line of research back in 2007 because at the time I was really fascinated with what you could collect with a device, and specifically traffic was an easy one. I think today there's a lot of other problems which are very interesting. One of them I'm currently working on is we're using these smartwatches to monitor Alzheimer's patients at home. It's a project which is very dear to my heart because I've had Alzheimer's cases in my family. And so one of the things we're very excited to do this summer is we're going to deploy smartwatches and sensors in a cohort of 300 patients' homes through the UCSF hospital. And again, using similar learning techniques, this time not to monitor traffic, but to monitor their activities. Another thing we did back in the days was we had one of the first apps to monitor earthquakes using smartphones. I'm really excited because 2 weeks ago it was finally launched in the T-Mobile store by the Seismolab, and there are hundreds of thousands of downloads. And so the Seismolab is now running a nice pilot using the iShake original prototype we had to use this for early warning. And then the last thing I'm still working on is just in the very same way phones can be used to monitor traffic, they can also be used to monitor water. So one of the things we built at Berkeley is a floating platform of 100 vehicles that collect data and transmit this to a backend server so we can reconstruct in real time what the flow of water is. And so these are, before we went to the actual field, what we do in the swimming pool to try them. We have a lot of nice outdoors swimming pool in California when the weather is nice. Sorry, I keep rubbing this in with the snow this weekend. And these things are kind of self-guided and they can transmit data in real time. And okay, just to convince you that California is a good place to be, this is what students do around this time of the year. So we basically dump them in the water, and then these things basically GSM back their position to our system. We have coordination control so that we can allocate the fleets, in a way that we can monitor. This is obviously accelerated. I mean, they swim fast, but they don't swim that fast. And then using ultimately the data to reconstruct the flows in real time to help the departments of water resources. So I think we've reached the end of the hour. I'm going to stop here. But again, I want to thank Azu and Monter, Ali, who is not here, and Pablo for this invitation. I'm very happy to be here, and thank you. Yeah.
So you omitted the prefix to Nash in all your slides. Is it always unique, the Nash equilibrium? Do you believe it's always unique in this network?
No, it's never unique. Well, no, I shouldn't say never say never, but it's not unique. I mean, there's many ways. So depending on the network loading, sometimes you can allocate flows so from an intuitive perspective, if, for example, a freeway is not completely congested and everybody is traveling at free flow travel time, it's very easy to reallocate people on two parallel freeways to get, so you absolutely don't have in the general case uniqueness of the equilibrium, which is why when we initially characterized that problem, so first I said chi is not known, or chi star is not known. It's gonna be there, okay. So chi star is not known. First, we don't even know it was a Nash equilibrium until we proved it, but then it's a set, it's not a value.
Yes. Okay. Hi. Thank you for the very good talk. A question on the behavioral side of things. With the mobile apps, we can know the routine trips only every day to Bayen, tomorrow, and so on. We can crawl the maps and ask provider 1, provider 2, what are the top 3 routes?
Yeah.
Do you have an idea of which percentage of the population take one at least, or any of the 3 recommended routes?
I don't know. But okay, I don't know. So I asked this question a week and a half ago to my student who runs traffic at Apple. So he looked at me with a smile and said, next question. So obviously, the key words here is basically how many people are using the apps, then how many people are following the apps, and then within the following the apps, which of the routes are you following?
And how this
Yeah.
affect the results?
Yeah. So I only have a vague answer to the first question. I don't know about the second question, and I have no idea about the
The
third
first
question.
one has been better. 5 cities, 18 months.
Yeah. Yeah.
Tell me what you're
No. I mean, I don't have scoop numbers to give you, but I mean, even when you talk to people at Apple and Google, the ranges you get are wide. And quite honestly, I don't know the answer to your question. I mean, I think it would be probably feasible to start to measure this, maybe, but I've not. This is not something I've worked on.
In fact, we don't know if they actually follow Google or not, but you can know if they take any of the 3 top routes the providers give you.
Yeah.
34% do not take any
They
of
won't
the
take
2
any.
providers.
Yeah, which is exactly why in that second part of the talk, which I didn't go in detail, I tried to have different populations. And the way we model this, though we don't have the numbers, but the way we model this without numerical values is basically some people will just use travel time as a value, and some, there is an aversion to using it. We just don't know how much it is.
They just do other things.
Yeah, they do other things, yeah. And we don't know how to put a numerical value on it. So we have convergence to the solution. We just cannot run numerical values yet. And we'd love to use your data if you have some. Yeah.
Yeah, so actually, very similar question to Marcus. If you think about each agent making the recommendations to the drivers may choose to take one of the three and so forth. So now the question becomes is how robust this iterative algorithm to, one can say maybe that some confidence that they take the recommendations that were given, but they shuffle things around and do nothing. And the question, can you analyze the robustness of your sequential game to see where you converge or if there's a convergence argument there with some errors and not necessarily following exactly the recommendation.
And the robustness would be specific to the user choice?
Yes. So basically you recommended certain percentages, but what was adopted was a different set of percentages.
Yeah, so obviously I've not done that. What I've seen happening at Facebook is, you all heard about, did everybody hear about the Adam Kramer case? Okay, so when there was this really made the news several months ago, almost a year ago now. There's a person named Adam Kramer who worked at Facebook, and he was running these experiments on the feeds where he wanted to investigate whether if you give people negative stuff on their feeds, they are likely to be more depressive or to do more negative stuff on their feeds, and if you give them positive stuff on their feed, whether they would be more upbeat. And it turns out that there was a really famous paper of his called, which appeared in PNAS, the Proceeding of the National Academy of Science, that showed that it is the case. So you can definitely see some correlation. Okay, so that's a more general, that's a very specific case of a randomized experiment that he was running at Facebook on the feeds. So the reason why I'm bringing this is if we wanted to assess the robustness of this framework based on user behavior, in essence, what Google or whoever would have to do is to run a randomized test on people, so sending you really bad routes to see how you react to really bad routes. You can imagine how popular that would be if it leaked, because in the case of Adam Kramer, it was basically, it made the headlines, like, imagine someone had committed suicide because of more negative posting on Facebook. In a sense, it's a real question. So the answer, again, to your question, I don't know the answer, but if I was going to run an experiment to do it, I think what I would do is the following, is I would basically start to send people some very specific information, bad or good, see how they react to it, so kind of probably compute some sensitivity, and then try to see how that fits in the algorithms. I realize it's not a very mathematical answer, because I've never really studied this, but just thinking aloud here, that's what I would do. And by the way, I'm pretty sure that every major company in this field is doing it. A lot of our students jointly work in these companies, so we talk about this with them. These randomized tests is just taking very specific users and changing the way the results of the searches on Google or the feeds on Facebook or whatever other products are out, and then just quantifying their reaction. So probably we're all guinea pigs here, we just don't know it. I hope it answers the question.